Okay, so today we're going to talk about water, and without a doubt, water is a compound that excites biologists and chemists more than any other, and it's probably the most important compound on our planet. And today we're going to talk about hydrogen bonding and why hydrogen bonding gives this compound its physical properties. So this is liquid water, pourable, clear stuff, and it's liquid at room temperature. So maybe it's 25 degrees in this room. I don't know, something like that, 22, 25 degrees. And it's liquid because the molecules bond to one another through what's called hydrogen bonding. So let's look at some representations of water. And remember, the formula of water is H2O. So there are two hydrogen atoms bonded to one oxygen atom. And you'll recall from our discussions of Lewis dot structures that the central oxygen atom is bonded in a configuration that gives the molecule a bent structure. So electronegativity differences between the oxygen and hydrogen give rise to bond dipoles. You'll also recall, hopefully, that electronegativity is the tendency of an atom to draw electron density towards itself in the context of molecules covalent bonding. So for example, that oxygen atom has a much higher electronegativity than this hydrogen atom. And so we can write a delta negative, a partial negative charge on this oxygen and a partial positive charge on this hydrogen. And that configuration gives this bond a bond dipole. So that's an electronegativity difference that gives rise to an asymmetrical distribution of electrons between the two atoms. And the negative end of the dipole is positioned where this arrow is. The positive end is where the hydrogen atom is, the lower electronegativity atom. This bond and this bond we can consider to be identical. So there's another bond dipole associated with this bond. These two bond dipoles add up, they add to one another to give a molecular dipole moment to this molecule. So we could draw that in a vertical fashion like this, where the negative end is up towards the oxygen atom, the positive end is down towards these hydrogen atoms. And this molecular dipole is what gives rise to the cohesive properties of water molecules. So if we write two adjacent water molecules, and we're imagining them to be adjacent to one another in a liquid sample, a moment within a liquid sample, we might draw the hydrogen bonding between them as this dotted line here. The partial positive on this hydrogen is positioned adjacent to the partial negative on the oxygen atom of a separate water molecule. So these non-covalent interactions can be reasonably strong, so strong that this is the primary reason that water has a boiling point of, say, 100 degrees instead of much, much lower. So the hydrogen bonding in water gives rise to its physical properties, or at least some of its physical properties. Now, remember, these representations of water, well, they're not so great. They're kind of like the notes on a sheet of music compared to the sound. The sound and the notes on the sheet of the music are very different. This might be a reasonable representation of water, but maybe this one's a little bit better. The physical model here, where the oxygen atom is represented by the red sphere and the hydrogen atom is represented by these white spheres. It's this structure and the electronegativity difference between these two atoms that give rise to the hydrogen bonding that we've talked about. So let's look at a few sort of molecular graphics representations of the different phases of water and talk about hydrogen bonding in them. So here's a representation of gas phase water. The water molecules represented by these spheres. And you can see their movement. You can notice, if you look carefully, they just bounce off of one another. They aren't sticking to one another. So in a gas phase sample of water, let's say this is at 1500 degrees centigrade, these water molecules are bouncing around with such high energy that the energy of the hydrogen bonding is just sort of minuscule. We don't even have to worry about it. So we see the water molecules bouncing off of one another as if they are not coherent, as if they don't stick to one another. And that again is because there's so much energy in the sample. They're just whipping around, flying around with such high energy, they don't seem to stick to one another in the gas phase. Here's a sample of a representation, at least, of liquid water. And now you can see that they're kind of sticking to one another. The sample doesn't fill the whole volume of the container, for example, and they're sort of sticking to one another. And that cohesive interaction now at a temperature below 100 degrees, now it's substantially strong compared to the energy of movement of the molecules. So the energy of movement of the molecules does not completely overwhelm the hydrogen bonding strength. And they stick to one another, and we have this condensed phase water sample, as you see here. If we drop temperature even further, we have ice, solid phase water. Now, the thermal energy of the sample is so low that it's not even high enough such that the molecules can move around relative to one another. They're sort of stuck in central locations. They might be vibrating or moving some, because there is some movement. We're not at absolute zero Kelvin here. There might be some movement, but now the hydrogen bonding strength, there are two important things about this. The hydrogen bonding strength of water is high enough that under the conditions we typically observe on our planet, we can have solid, liquid, and gas phase water. That's extremely important because biology, geology, earth science, atmospheric science, none of it would work the way it does were it not for this hydrogen bonding that makes things like ice form at 0 centigrade. Another very important property of water, as it relates to hydrogen bonding, is the fact that when the water molecules hydrogen bond in solid phase water, there are little pores, essentially, that open up in the solid phase water, and the stuff expands. Most materials contract when they're cooled down and they freeze, but water does the opposite. It expands. Now think about, if this didn't happen, ice would crush fish in the winter up here in Montana when the lakes freeze over. The ice floats to the top of the lakes, insulates the lake from the colder atmosphere, and in fact, there is an environment where aquatic life can exist because of the hydrogen bonding. The way those angles in the water are, the water molecules, the oxygen and hydrogen angle, the stuff opens up a little bit, boom, we have less dense material at the top, we have an insulating layer, and all the sorts of properties that water display, you could tie into most of the chemistry and biology that we observe onto the planet, all the way back to this hydrogen bonding stuff. So, first thing is, electronegativity difference gives rise to bond dipoles. Bond dipoles, when they involve oxygen, hydrogen, water, they give rise to the hydrogen bonding, and the physical properties that we've talked about today are rooted in the hydrogen bonding of water molecules.